The final section of Mastery Quiz 3 is dealing with molar volume of a gas, which is section 4.3 in your textbook and in your demands. Molar volume is dealing with a mole. So just as a review, a mole is a term that's used to represent the number 6.02 times 10 to the 23, which is the amount of any substance containing that many particles. This number is also known as Avogadro's number. Molar mass is what we've used a lot in Chem 20, and it's the mass of 1 mole of a substance. And molar mass we find on the periodic table. For example, molar mass of magnesium is 24.31 grams in every mole. The units of molar mass will always be grams per mole. In our last mastery quiz, we talked about how Boyle's and Charles' law can be combined to make the combined gas law. Really, the combined gas law is a bit simpler to use because it's using all of the terms of pressure, volume, and temperature. In this section, what we can combine is the concept of Avogadro's theory and the mole. And what those combine to make is the idea of a molar volume. If you remember from last video, Avogadro's theory is that equal numbers of gases at the same temperature and pressure will have the same amount of molecules or the same amount of entities. What that means is that if we have a gas at the same temperature and pressure, there will be a certain volume, and that is the molar volume, because we know that if we have the same amount of molecules, those molecules will have the same volume as long as they're a gas. So the definition of molar volume is the volume that 1 mole of gas will occupy at a specified temperature and pressure, and that will be for all gases. So molar volume will be the exact same for all gases that are at the same temperature and pressure. The reason that it is the exact same is that all gases have the exact same physical properties. We have 2 molar volumes that we need to memorize, and that's the molar volume at STP and the molar volume at SATP. At STP, we will have 22.4 liters in every mole. And a reminder that STP is going to be 101.325 kPa and 0 degrees Celsius. At SATP, your molar volume will be 24.8 liters per mole. And a reminder that SATP conditions are 100 kPa and 25 degrees Celsius. We can use these values, these molar volumes, as conversion factors, just the same as we use molar mass as a conversion factor. If you look at this diagram down here, this is the volume of 1 mole of gas at STP, which would be about 11 empty 2-liter pop bottles. This molar map is one that we've used before. So on the left-hand side, you can see here that going from mass to moles to particles, this is what we've done in Science 10 and in Chem 20 so far. So we're going to use our molar mass in order to get from mass to moles. We would use Avogadro's number in order to get from moles to number of particles. In our solutions unit, we did the top branch, which is going from moles to concentration. Going from moles to concentration, we're either using C equals N over V, or we're using our concentration, which is moles per liter. What we've just added on today is the bottom part that I'm putting in blue. So we can go to the gas volume at STP using 22.4 liters per mole, which is our molar volume. We can go to our gas volume at SATP using 24.8 liters per mole, molar volume. Note, the units for molar volume will always be liters per mole. So moles are on the bottom. Similar to molar mass, it's grams per mole, moles on the bottom. We are dealing with molar volume instead of molar mass because it's way easier to measure the volume of a gas than the mass of a gas. Calculations with molar volume we can do using unit analysis or proportions, like most calculations we've done so far this year. So I'm going to do the first one using unit analysis and the second one using proportions. The first example here, you'll see that we're looking for volume, and we're starting with moles. So I'm going to write down what we're starting with. So we have 0.024 moles, and I'm going to have to multiply it by my conversion factor at SATP. So at SATP, I'm looking for, my final answer is going to be in liters, which means I have to put my liters on the top. So I have 24.8 liters for every 1 mole. And then when I'm doing unit analysis, my moles and my moles will cancel out, which means the only unit I have left is liters. So the answer that I get there is 0.05952. Significant digits wise, I need to give 2 because I had 2 in my question, which means I'm going to end up with 0.60 liters. The second question is looking for chemical amount. Chemical amount is the same thing as moles. It's asking for STP, and what I know, again, I'm going to do this one using proportions. What I know at STP is that I have 22.4 liters in every 1 mole, which means I can set it up equal to 5.6 liters in X moles. Here what I would do is do 5.6 multiplied by 1 divided by 22.4. My answer here would end up being 0.25 moles. In this question, it's asking for volume of a gas, but it's giving us grams. So you can see here I've written down my grams to moles. In order to get grams to moles, I'm going to have to use my molar mass, and then I'm going to have to use moles to liters using my molar volume. So I'm going to start with my 3.50 grams of helium. And I know that what I'm looking for in my first answer here is I'm looking for moles, which means my moles needs to be on the top and my grams needs to be on the bottom in order to get moles as my answer. I know that I'm going to have 4 grams for every 1 mole, which means my grams will cancel out, and then I'll have my only unit left is moles. My answer there is 0.875 moles. And again, you don't have to find your answer there. You can keep on going to find your final answer if you want to. My second step here is going to be going from moles to liters, and I'm going to be using my molar volume, which is at SATP. My final answer here is going to want to be in liters, which means my liters needs to be on the top, and my moles needs to be on the bottom. I'm going to have 24.8 liters for every 1 mole, which means my moles will cancel out, and I will be left with my liters. My final answer in this example would be 21.7 liters of helium. This example is similar to the last one. It says a propane tank for a barbecue contains liquefied propane. If the tank mass drops by 9.1 kilograms after a month's use, what volume of propane was used? So what that means we used was 9.1 kilograms of propane. So similar to the last example, we first have to go to moles, then to liters, which means I'm going to start with my 9.1 kilograms. And my first step is to use my molar mass in order to get to my moles, which means I'm going to have to divide by my 44.11 grams in 1 mole, and my grams will cancel out. My answer here would be in kilomoles. So I would do 9.1 divided by 44.11, and that would get me the answer of 0.206 moles. If you're doing this in 2 steps, you would stop there, and then you would take your moles on to use your molar volume. I can also do it in 1 step, however, and my 1 step means that I would just multiply on, and I would use my molar volume here. And in the end, what I want to do is I want to get liters, or volume. This is at SATP. I have to cross out my moles, and I'm looking for liters, which means I have 1 mole in 24.8 liters. My moles and my moles would cancel out, and I'm going to be multiplying my 0.206 moles by 24.8 liters, and I would get 5.116 liters. The trick here is that we never crossed out our kilo, which means this is going to be in kiloliters and not liters. The second question here, what if I wanted your answer in liters? We could do 5.116 kiloliters, and we can use the conversion factor that we know we have 1 kiloliter for 1,000 liters, which means the kiloliters and kiloliters would cancel out, and our answer would end up being 5116.3 liters. In this question, however, because it gave me 2 significant digits, I need to put this into scientific notation, which means I would have 5.1 times 10 to the 3 liters. In summary, molar volume is a conversion factor that we can use to figure out the volume that 1 mole of gas will occupy at a specified temperature and pressure. And our molar volumes at STP is 22.4 liters per mole, and at SATP is 24.8 liters per mole.